здоровья. Но вы их берите. Да, могу сказать что-нибудь. Есть. Ну хорошо. Then let's start. So as I promised, we start from scratch, and I apologize to those of you who know this already. If you do know, then you may safely adjourn till February, when we compute characters of symmetric groups. But if you do not know, then you are strongly advised to learn the basic representation theory, like I don't know what, orthogonality of characters, induction of finite groups, I mean, over complex numbers, number of representations, the sum of squares of representation dimensions, some basic things like this. Okay, and we will certainly consider partitions. So it's a collection of positive integers. Like this, ordered, and then the sum of lambda i's n well, is called the total volume of corresponding Young diagram, and L is the length of lambda, and well, this is the same as Young diagrams. But there are at least three common ways to depict Young diagrams, probably called English, French, and Russian. And we will follow MacDonald notation, so probably it's English, I guess. Something like this. So we'll draw it like this. And this corresponds to lambda equals 6, 3, 2, 1. And then this will be drawn on a coordinate plane. So this will be coordinate j, and this will be coordinate I. And then there is transposition. Lambda transposed, well, just we reflect it in the diagonal, so we get what? It's 4, 3, 2, 1, 1, 1. Okay, and there's another common notation for this. It's 4, maybe to power 1 if you wish, 3, maybe to power 1, 2 to power 1, but then 1 to power 3. Okay, and these are all standard notation we will always use. Any question? So now symmetric functions in k variables. Well, we just consider polynomials in x1 and so on, xk, and then take invariance of the symmetric groups. Okay, and well, among those, there are elementary symmetric functions. So, as we already discussed last time, it's the sum of all variables, and E2 is the sum over all pairs I not j, xi, xj, and E3 is the sum over all triples I not j, not L, xi, xj, xl, and so on. And then finally ek will be just the product x1, xk. Okay. And then it is known that they generate the whole ring, but we will reprove it today. So the basic fact is that this ring of symmetric polynomials is just the ring of polynomials in E1 and so on, Ek. Okay. Now, if we have even more variables for m bigger than k, we have a homomorphism from polynomials in n variables onto the ring of polynomials in k variables, very stupid one, namely x k plus 1 and so on, xm, all go to 0, and x I goes to xi if I is less than or equal to k. Okay, this is called row mk. Pardon me? Yes? Yes, there is such a restriction homomorphism. From my head, just given any m bigger than k, there is such a restriction homomorphism, and if you restrict it to invariance, certainly it takes invariance to invariance. Like this, to invariance, and again it is surjective. So this row mk preserves degrees. So we will, from now on, we'll consider only its symmetric version, and we'll forget about the thing it arose from. So this notation is for restriction of symmetric functions, and it preserves degrees and is an isomorphism in degrees less than or equal to k. For example, from this fact, just because the restriction of EI is EI for I less than or equal to k, and 0 otherwise. Okay, so this ring lambda ubiquitous, we discussed the whole time last Tuesday, is defined as the limit, inverse limit of this system. With respect to the transition maps rho mk. Okay, so then, well, it is generated by those elementary symmetric polynomials. This is the fact we still did not prove yet, but we'll prove momentarily. So there is a tautological base of lambda. Well, it's also homogeneous. Well, in fact, all the bases we will encounter will be homogeneous bases. And this one is comprised of monomial functions m lambda, numbered by partitions. Well, it is m lambda is x1 to lambda 1, x2 to lambda 2, so on, xl to lambda l. Well, I erased my typical partition diagram. Well, symmetrized like this. So maybe the scientific definition of symmetrization is take the sum over all permutations, but that's not what I mean. Because, for example, if I take x1 to power 1 times x2 to power 1, and so on, just product of x's, and try to symmetrize it, I will acquire some L factorial, yeah, from summing overall permutations. But I don't want any coefficients. All the coefficients are just 1. All monomials are permutations of this one, and all coefficients are equal just to 1. So, for example, M1 is what? No, it's x1 plus so on, like plus x2 plus x3 plus so on, and this is just E1, right? And what is M11? Right, and so M1 to n is En. And what is M2? Just for a change. Well, maybe that's true, but we don't know yet what is H. Just explicitly, what is it? Yes. So it's rather called P2, power sum. So in fact, Mn is Pn. Power sum, yeah. Fine. So this is just tautological base. By the very definition of symmetric functions, these guys form a base. There is nothing to prove. There is something to prove about elementary symmetric polynomials, but it's evident for these. Now, if we want to prove something about elementary symmetric polynomials, we want to produce a base. And the base produced from EIs is E lambda who? E lambda or who?
Yeah.
No, those guys. Oh, sorry. Sorry, I should have written here SM. Yes, thank you. These are symmetric functions. I'm sorry. So E lambda is just E lambda 1 times E lambda 2, and so on. Well, in fact, also we could define P lambda by the same formula. It's P lambda 1, P lambda 2, and so on. But these only form a base over rational numbers, not over integers. And while we are introducing notation, let me introduce the complete homogeneous symmetric functions H n. So it is the sum over all partitions of n of the corresponding monomial functions. So for example, H2 is P2 plus E2, right? Because there are just two partitions of 2, this one and that one. And then again, H lambda is H lambda 1, H lambda 2, and so on. So now let's prove that the elementary symmetric functions really do generate the whole ring. It will be our first lemma. That if we consider this guy, but for transposed partition, it will be equal to m lambda plus certain sum of a lambda mu and mu for mu less than lambda. In which sense? Or maybe I should write it this way. Mu less than lambda in lexicographical order, which means that mu should be less than lambda, right? Which means that mu1 is less than lambda 1, or mu1 is equal to lambda 1, and mu2 is less than lambda 2, or mu1 equals lambda 1, mu2 equals lambda 2, and mu3 is less than lambda 3, and so on. Yes? It's I think so, yeah, it's called linear, yeah, or total, I forgot. Complete order. Just the notation mu less than lambda like this is reserved for the so-called dominance order, which means that mu1 is less than or equal to lambda 1, or maybe I should write like this, then mu1 plus mu2 is less than or equal to lambda 1 plus lambda 2, and so on. And finally, the total volume of mu is equal to the total volume of lambda. So this is clearly not complete, not a linear, not a total order. Okay. So somehow this makes much more sense. Somehow, we'll see it many times in this course. But to start with, we use this stupid lexicographical order. Okay, so we will prove this lemma, but at least immediately it follows that those E lambdas form a basis of our symmetric functions ring. Just because we know this about M lambdas, and well, up to this renumeration, reindexation, transposition, they are related by a lower triangular matrix, strictly lower triangular matrix. But maybe I should say that those coefficients are all integers, and in fact even non-negative integers. Okay, so let's prove it. Well, let's write the transposed partition in the form I to some power. So multiplicity is mi. So 1 with the multiplicity m1, 2 with the multiplicity m2, and so on. And then mi is lambda I minus lambda I plus 1. Then this elementary guy is e to m, sorry, e1 to power m1, e2 to power m2, and so on, just by definition. Well, just expanding this product, we get x1 to the power m1 times x1, x2 to the power m2 times x1, x2, x3 to the power m3 plus many more terms, but this term is the leading one, so to say. So this will be, if we collect the powers of x1, we get x1 to the power lambda 1, x2 to the power lambda 2, well, x3 to the power lambda 3, and so on, plus all the permutations. So this x to the power lambda plus things, and well, the other summands are just permutations of this one, plus the other guys that are smaller in the lexicographical order. That comprise m lambda plus still other subunits that comprise m mu for mu lexicographically smaller than lambda. Yes. Well, maybe if I underline it, it's just this, just a monomial. Like this. No, why? No, just this is the sum of all variables, right? x1 plus x2 and so on. And then you raise it to power m1. This is the sum of all pairwise products of distinct variables. And then you raise it to m2. So these are not monomials at all, but I extract from them the lexicographically highest monomial. Okay, so we are done with this. Now we had all the other guys, E lambda, M lambda, H lambda, P lambda. And turns out that H lambda and E lambda are very similar, though they don't look like very similar at the first glance. So let's study the complete functions. Well, we introduced the generating function. H of t. T is some extra variable, is the sum over all positive integers, hr, this complete function, times t to the power r. And then the usefulness of this generating function is in the fact that it can be written as a product. Well, for example, let's consider E of t. It is also the sum over all non-negative integers. ER maybe, well, again, ER t to the r. And then what is this? This can be very easily decomposed into product. But you neglect tangerines. That's a big mistake on your part. You never know what you will be graded for. Pardon me? Почему вы не едите мандарины? Well, I claim that this sum is equal to a certain product of linear terms. So which product? Right. So the product over all I, 1 plus xit. Right? And here, right. So it's again the product over all I, 1 minus xit inverse. Yeah? Pardon me? H was sum of all m's. Hn is the sum of mu lambda for m lambda over all lambda partitions of n. Okay, so from this we see that that the product h of t times e of minus t is just 1. Okay, and well, this can be rewritten additively as the sum over all r from 0 to n minus 1 to r e r h n minus r is 0 for n strictly positive. Okay, and well, as a corollary, we can define an involution omega that I mentioned last time, a homomorphism. Omega takes ER, well, it's from lambda to itself, takes ER to HR. Well, since our ring is just a free commutative ring in generators ER, we are free to choose the values on ER just whatever we like. And we choose it this way. But then because of this relation, which is symmetric in E and H, it follows that, well, from here you can derive corollary that omega of HR is ER. So in fact, omega is an involution. Okay, maybe it's one thing, and the other thing is that lambda is the free polynomial ring in H1, H2, and so on. Okay, and now let us prove some horrible determinantal identity. But it will prove very useful later on, in particular for characters of symmetric groups. So we fix some n. Well, it's a typical argument in the combinatorics of symmetric functions. We fix some number of variables, prove something for this particular number of variables, and then this number of variables goes to infinity, and we get something for the whole ring lambda. Because the ring lambda itself is the limit of it takes generators ER, the elementary symmetric functions, to the complete homogeneous symmetric functions HR. Pardon me?
So we just
Here's the definition. It is defined on generators. And once again, since there are no relations between them, where we can send them wherever we like. Okay, so we fix some number of variables and consider matrices H with matrix elements H I minus J for I and J between 0 and n, and also E. Again, well, minus 1 to I minus J because of this. E, I minus J for I and J between 0 and n. Then, by this basic identity, those two matrices are inverse to each other. And maybe to begin with, they are strictly lower triangular. Yeah, because if I minus j is 0, we just get 1. And if I minus j is negative, we get 0. So two strictly lower triangular matrices are inverse to each other. Okay, well, this means that an element like, say, Hij can be expressed through elements of this matrix. And how can it be expressed? An element of the typical element of this matrix at the ith row and j column. So I guess you must know the formula for inverse matrix. By the way, since they're both strictly lower triangular, the determinant of H is equal to the determinant of E equal 1. Yeah, and now Hij is what? Yes. By this formula? Right, but the determinant is 1. So I think it's called algebraic complement over, well, Ij in the matrix E, but transposed. Right? This is the formula for inverse matrix. In general, you have to divide by determinant. By determinant is 1. You do know this formula. Everybody knows this formula. Good. Does everybody know its generalization? Not for just, well, this algebraic complement is a minor, n minus 1 by n minus 1 minor, right? Times minus 1 to I plus j. Right, and you can, well, this is symmetric relations, so if you consider such a minor of this matrix, its algebraic complement will be the corresponding element here. And it works for arbitrary minors. Yeah, do you know this? No? Okay, let's discuss linear algebra. So more generally.
I'm sorry, you mean Hij is one-dimensional minor of
Hij just is a matrix element, but it is a 1 by 1 minor, and what I'm about to say is that this generalizes for arbitrary minors. Not just 1 by 1, but anything by anything. Given two cardinality n subsets, like capital I, capital J, of our indices. Oh no, sorry, it starts from 0. I'm sorry, starts from 0. Yes? Произвольные. Arbitrary cardinality n, small n subsets. So given this, we can take the corresponding n by n minor h I j, and then well, it will be equal to the corresponding minor in the transposed matrix of E, just of the complementary sets I bar, J bar. Okay, and there will be also -1 to certain power, just the sum of coordinates there, here. Well, I don't know how should I say this. I plus J, so to say, if you know what I mean. Okay, and why this is so? Let's take a digression on linear algebra. Anybody knows? Nobody knows at all? Well, and what is determinant? What is the definition of determinant? Right, absolutely, right. So we have, well, there's an unfortunate clash of notation. So there is C n plus 1, and there is an operator E. Well, E is also bad notation. Everything is bad. H. There is an operator H. And then, as Leonid suggests, we should consider the Grassmann algebra. Or also, it's called exterior algebra. So everybody knows what this is? Yeah, good. Well, in particular, there's a top component. There's just one-dimensional space. And this is a functorial construction. So in particular, there is an exterior operator lambda h acting here, and there is an operator n plus 1 exterior power of h acting here. But since it is just one-dimensional space, this action is just multiplication by a constant. So what is this constant? Pardon me? Right, the determinant. And this is the well, intelligent definition of determinant, which, for example, makes it evident that a determinant of product is product of determinants, right? Just by functoriality. Yes, yes. Any linear operator in one-dimensional space is multiplication by a scalar, and this scalar is the determinant of H. And for this reason, the determinant of H1, H2 is determinant of H1 times determinant of H2. Well, because it's smaller than determinant. It's a small determinant. Minor is something small. Right? It's determinant of smaller size, by definition. Right? No. It's not minor, but it's minor. To distinct. Right, major, minor, right. Okay, and so H I J is a matrix element over lambda n h. Right, by the very definition. There are many matrix elements. They are all numbered by pairs of cardinality n subsets. Okay, and what do we know? We know that this is an algebra. In particular, there's a product from lambda n c n plus 1 times lambda n plus 1 minus n c n plus 1 to lambda n plus 1 c n plus 1, which is one-dimensional. And this product is a perfect pairing. With basis well, I don't know, ci almost dual to each other. Almost means up to sign. Okay, and well, this implies what I said before. That the matrix element with respect to this base is the matrix element of the inverse matrix with respect to the dual base, but this must be transposed because it's dual base, and also there is some sign, and also you must multiply by the determinant of h, because the pairing goes not to really scalars, but to really things where h acts by determinant. Right. Perfect pairing, non-degenerate. There is no kernel. They have the same dimension, and well, this pairing identifies this with the dual of that, and this with the dual of that. No kernel, non-degenerate pairing. Okay. So, well, let's come back from our digression. Yeah. So what do I want to say now? I want to say that back to our symmetric functions, elementary and complete. So given two partitions, lambda and mu, such that the length of lambda and the length of mu is less than or equal to a certain p, and the length of lambda transposed and the length of mu transposed is less than or equal to a certain q. So it means that both lambda and mu fit into a p times q box. Okay. And also, finally, suppose that P plus Q is equal to n plus 1, the size of this matrix we discussed. Now, we consider the minor over this H matrix with rows numbers lambda I plus P minus I, and volumes mu I plus P minus I. Has the algebraic complement in E transposed, well, with rows P minus 1 plus J minus lambda J transposed, 1 minus J, 1 less than J less than Q, and columns P minus 1 plus J minus mu J transposed. Okay, this is the claim we want to prove, and since we know that the complementary minors do coincide, the only problem is to recognize that those two minors are really complementary. That if this is I J, then this is I bar J bar. Yes. No, I think it is correct as stated. So anyway, the number of I think it's correct as stated. Why not? P plus Q is n plus 1, so they are really of, they're, well, claimed to be of complementary sizes. We must prove it, but we need to check that this set is the complement of this set, and this set is the complement of that set.
Is it an exercise from the first question,
From first what?
From first onward.
Maybe, I forgot. Is it really? Is it?
Not quite like this, but
No, I'm absolutely fine if you consider it as an exercise, and moreover, if you already solved it, I'm only happy. So, I mean, shall we go over it, or shall we dismiss it? Pardon me? Okay.
so is it impossible because it is Hooke function?
Pardon me?
If we equal something from, в общем,
Да.
они, правда ли, что вот они пересекаются тогда и только тогда, когда Hooke function на какой-то диаграмме какого-то элемента равна нулю?
Ну, они не должны пересекаться вообще.
Ну вот они пересекаются, и если они пересекаются, то вот...
Yeah.
ну, в общем,
Certainly all hooks are positive, yeah. But still, we should solve it, yeah? So, maybe I should call it I, j, I prime, j prime. That I prime is the complement to I, and j prime is the complement to j. So this is called lemma. Maybe two. So let Q be at least lambda 1, P at least lambda 1 transposed. Then the n plus 1 integers lambda I plus p minus I 1 less than I less than p and p minus 1 plus j minus lambda j transposed. J goes from 1 to q. Form a permutation over the set from 0 to n. This is for rows and similarly for columns. Okay, so this proves that I prime is I bar. So the proof, we know that lambda fits into q to the power p. It's the p times q box, and we number, maybe we index the segments of the boundary of lambda in this box by indices 0, 1, and so on, starting from the lowest. I mean, this is our lambda. This is our box. Well, there is no colored chalk, but this is the big ambient box. And well, this will be 0, 1, 2, 3, 4, like this, yeah? 0, 1, sorry, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. Yeah? Starting from, yes, starting from the bottom. Okay. Now the vertical segments are indexed by lambda I minus so plus p minus I, I between 1 and p, since the segment intersecting the ith row has lambda I horizontal segments preceding it, and p minus I vertical segments preceding it. Pardon me?
Откуда вот первое предложение берется? Казалось бы, они там ничего не чисто.
Well, it's just because
А вот это должно быть не 4, а 4, 5. Вот эти segменты разделены два, потому что
just one moment. So how many do we want? We want yeah, maybe you are right, because we want n plus 1 altogether, yeah, and n plus 1 is p plus q. Yeah, so it's the total number of the boundary. Right. So you are right. It's 4, 5, and 6. And or maybe even maybe even we should start here. Maybe this should be 0, 1, 2, 3, 4, 5, 6, 7, 8, and then here 9. Zero is okay. Thank you. So yeah, now taking the transpose we see that the horizontal segments are indexed by the indices q plus p minus 1 minus lambda j transposed plus q minus j, which is nothing but P minus 1 plus J minus lambda J transposed for J between 1 and Q. Okay, and we're done. Pardon me? Yeah, P minus 1 plus J minus lambda J transposed. Okay, so all in all, we get that the determinant of matrix with the matrix elements H lambda I minus mu J minus I plus J for I and J running between 1 and P is equal to the determinant, or maybe the sign. The sign is minus 1 to the power size of lambda plus size of mu. Determinant of matrix with matrix elements minus 1 to lambda I transposed minus mu J transposed minus I plus J, and here E lambda I transposed minus mu J transposed minus I plus J. And here I and J run from 1 to Q. And now the signs here are just products of certain signs for columns and for rows, so you can extract them, and after this they will cancel out that sign, and we will have that the determinant of H lambda I minus mu J minus I plus J is equal to the determinant of E lambda I transposed minus lambda J transposed minus I plus J. Okay, and finally we can specialize to mu equals 0, and this will be the identity that we will profit from later on. So for mu equals 0, we get the determinant of H lambda I minus I plus J is equal to the determinant of E lambda I transposed minus I plus J. Okay, so this will be used later on. And still we have 10 minutes, so let's do something about power sum functions. They canceled, this minus 1 cancelled with this minus 1. Well, maybe that's really an exercise. As I said, you see that this is the product of something depending on I and depending on J. So there is some product of minus 1 for rows, and for columns they can be extracted, and if you extract all of them, you just get this. I mean, just because, well, okay. So the power sums we already defined. PR is the sum of xi to the power r. It's mr, as we already discussed. And now, again, let's consider generating function. P of t equal to the sum from r at least 1, pr to t r minus 1. And note that there is some difference from what we did before. Before it was of different homogeneity degree. Yeah, we had like er to t to the power r, and now it's t to the power r minus 1. And also r starts from 1, not from 0. Well, let's rewrite this as the sum over all i's and over all power r, xi to the r t to r minus 1, and then this can be written as the sum over all I, xi over 1 minus xi t, right? And this can be interpreted as a logarithmic derivative. Of 1 over 1 minus xit. So then this is the logarithmic derivative of the product. 1 minus xit inverse. And this is the logarithmic derivative of you know what? Pardon me? Right, ht. Right. Okay, so this is h prime t over h of t. And similarly, you can relate it to the generating function of elementary symmetric functions. And this way, you can express both e and h via t, and conversely, p of minus t is the logarithmic derivative of e of t. So e prime of t over e of t. So we get nhn equals the sum of p r h n minus r, and also n e n is the sum of -1 to r minus 1, p r e n minus r, and these are called Newton formulas. So in particular, you see that if you invert all the integers and obtain rational numbers, then over rational numbers, those p's generate the whole ring as well. Yeah. And p lambda is p lambda 1, p lambda 2, and so on. those guys form a Q basis over lambda Q, say H2 is equal to P1 squared plus P2 over 2. And well, we know that our involution omega permutes H of t and E of t. And we know that P of t is, well, P of minus t is the logarithmic derivative of E, and P of t is the logarithmic derivative of H, which means that omega of Pn is equal to minus 1 to n minus 1 Pn. Okay, and well, this means that omega of P lambda is epsilon lambda P lambda, where epsilon lambda is the sign minus 1 to the power size of lambda minus length of lambda. Okay. Well, maybe I have to stop. So I have a few more words to say about power functions, but this will require certain knowledge about symmetric groups, like the sizes of centralizers of cycles. So we'll start from it next Tuesday, and then move on to Schur functions. Yes? So they were certainly discovered by Newton, and what do you mean by interpolation polynomials? There is Lagrange interpolation polynomials, and maybe I just don't know. I'm sorry for my ignorance. I only know Lagrange interpolation polynomials, not Newton ones. Sorry. So that's it for today. Thank you.